Good morning. Hey, it's April 6th and back for another edition of Kitchen Table Chemistry here. It is Monday, and what we're going to try and do today is spend our time looking at rate laws again and determining the order of a reaction. I'm going to spend this video effectively just going over the practice problem that I gave you on Friday and going through the different steps of it and hopefully clarifying things. I'm certain there are questions out there, but let's see how it went. First of all, remember a rate law is going to look like this. Rate is equal to K times the concentration of A and then B. In this case, our rate law is going to end up being K times the concentration of NO, which was the first reactant, to the M, times the concentration of O2, the second reaction, to the N. So this is what we were trying to figure out. Now, the first thing we're going to do is figure out the rate orders for the nitrogen monoxide and the oxygen here. So flip forward, and here's the data that was given to us up at the top. The first thing I want to do is I want to get the rate order for the nitrogen monoxide. So I want to take a look at here experiment number 1 and experiment number 2, because in that, this was held constant. The oxygen was held constant and therefore can be eliminated. So any change in the rates here is going to be due to the change in the concentration of the nitrogen monoxide. So I will take a look at experiment 2 over experiment 1, and that is equal to K over K. Hold up a sec. Getting ahead of myself. Sorry. My bad. That is equal to the eraser here. And we'll go to the screen, is equal to the rate, I don't know why it's doing that, the rate 2 over the rate of 1 is equal to K over K, which we don't know. And then we have our two substances here. We have nitrogen monoxide, concentration from the second, and that is to the power of M, over nitrogen monoxide from the first experiment to the M. And then we have the oxygen here to the N, and the oxygen to the N as well. So the rates then, when we put them in, will be equal to, don't do that, 1.0 times 10 to the negative 4 over 2.5 times 10 to the negative 4 is equal to K over K, which we don't know, and we're going to be able to cancel out anyway. And our concentrations here will be 0.02 over 0.01, and this both times is going to be to the M. And then here is going to be 0.01 over 0.01 in both cases to the N, but we're going to be able to cancel these out completely. So the K's cancel out as well, and what I end up with then is effectively 4, and I did copy this down wrong. This is 2.5 times 10 to the negative 5. So this is going to end up being 4.0 is equal to 0.02 divided by 0.01 gives us 2 to the M, and that 2 to the M means that M has to be equal to 2. That is the power that will be raised to. So now I know that this is a second order. Now let's figure out the rate, or let's figure out what it is for the oxygen. Now to do that, let me figure this out here. There we are. I'll just erase what I did. You can always go back and look at it again. Probably easier that way, and it's probably an easier way of erasing it. Okay, once I've got this all erased, what I'm going to do is go back and I want to figure out the rate order for the oxygen. Now the rate order for oxygen, yeah, erase all link on slide. Yeah, next time see that, dimwit. Okay, so here we'll go over here, and what we'll do is we're going to compare, I think, now experiment 3 and to experiment 1. If we do that, that will allow us to get rid of the nitrogen monoxide. Although we know it's rate order, we don't necessarily need to have that. So we're going to put here, we're not going to do that. Okay, so now what we're going to do here is we're going to put experiment 3 over experiment 1, and that will equal the rate from 3 over the rate from 1, which will equal, again, the K over K, concentration of nitrogen monoxide here in the third, and that would be to the second order because it's second order, over nitrogen monoxide in the first to the second order. And here it would be the oxygen, we just want to go with what it is, to the N over the oxygen to the N. And this would be for the third, and this would be for the first. When I fill in my values, the rate of 3 is 5.0 times 10 to the negative fifth over 2.5 times 10 to the negative fifth. So that's going to give me a nice even 2 is equal to K over K. Again, we haven't found it, but we'll find it in a second. And then here we have the 0.01 squared over 0.01 squared, so they will cancel. And then we have 0.02 concentration to the N divided by 0.01 concentration to the N. So that's going to give us 2 will be equal to 2 to the N. Therefore, the power of N is equal to 1. And now we have the rate order. That's a 1. That's a 1 like that. So now we have the rate order of our two reactants here. So our rate then will be equal to K times nitrogen monoxide to the second, oxygen or O2 to the first. All right, that looks like kind of junky, but you got the idea. All right, next idea. What is the concentration of NO when it is 0.015? Okay, the first thing we need to do then is to find K. In order to do that, the rate is equal to K times nitrogen monoxide to the second, O2 to the first. So I'm just going to pick any one of these three things. And in this case here, I'll pick 1. And I'm going to put in what these values are. And then the only thing that won't be there is K. So what I will put in then is 2.5 times 10 to the negative 5 is equal to K times 0.01 concentration squared times oxygen here, which would be 0.01 to the first. And I did this and I solved for K, and I got a value for K of 25. The actual units for this, because this is what is called a third order, where do I get, stop it, where do I get third order from? Stop it. All right, just about getting ready to quit here. Don't do this on me. Where do I get third order from? Well, third order comes from this. And that third order comes from this is 2 and this is 1, and you add them together and it makes third order. So if it's third order, what we're going to want to do is take and do this over molarity squared, stop it, times seconds. So molarity squared times seconds. That molarity squared times seconds is the squared because it's third order altogether. So that's why it's molarity squared times seconds. And that and the time is just seconds. So there we are. So that's our K value. Because we know our K now, what we can do is solve for the rate. So the rate will equal 25 over molarity squared times seconds times, and we're looking at this concentration of 0.015, and that would be 0.015, and that would be squared, and then times 0.005 for the oxygen, and that would be to the first power. And I did this before, and I got a rate of 2.8 times 10 to the negative 5, and that's over molarity times seconds. So that would be the rate that you would get, and that when you put your K value in there. Again, that's the joy, or the what's cool about rate laws, is that once we figured out what this rate law is, as long as we know the concentrations of these two things, we can figure out what the rate of the reaction is, and that's the power of kinetics and of developing a rate law like this, because it gives you this ability to just know how fast it's going to go under these conditions. Uh, Now, the last part here was just a simple add-on. It's a relative rate. So you've got this rate that's 1.0 times 10 to the minus 4. And this is for the nitrogen monoxide. And because it's relative rate, if you think of the reaction is 2 nitrogen monoxide plus O2 yields, all right, I ran out of space. 2 nitrogen monoxide plus O2 yields 2 nitrogen dioxide. We're simply going to use the coefficients here. And by using these coefficients, that's going to let us, this coefficient 2 here and this coefficient 2 here, that's going to let us solve this. So it's a relative rate problem. So we have 2 NO2, and the unit will be moles, over 2 moles of the nitrogen monoxide. And it's not going to change a darn thing. So it's 1.0 times 10 to the negative 4, but now it is the rate for the nitrogen dioxide appearance. So this, again, it was a relative rate problem, and that, because it said relative rate in the question, you can simply go back and solve it like this if it's a relative rate problem. Okay, I hope this solution was helpful. I think it might have been. Otherwise, send me questions, and send me emails or whatever kind of issues you're having. And that I'm really, really curious as to how this is going along, teaching it to yourself, and that I'm really only having the videos to go with. Some of you are probably very, very quick at it, and some of you probably are still kind of in the struggle stage. I'd like to get everybody together, and so to do that, I've got 2 practice problems for you to take a look at. They won't be due until Tuesday night midnight, give you a chance to take a look at them. They'll also be the first thing on the 4th marking period, your final marking period, and they're worth 20 points. So I hope you're going to have a decent time with them, and I look forward to seeing them from you. This is all, and I'm signing off for today. Take care, and the next time I talk to you, it will actually be Wednesday, and I'm going to show you a little bit more with this, and then get a little bit into integrated rate laws, but mostly just still on developing a rate law. Take care. I hope you're doing well. Signing off. Bye-bye.